Okay, any question about the previous session? In the previous session, we talked about energy-based models, and we also see the one algorithm to sample from these models. We see that the most challenging part is the calculation of the partition function, which is the normalizer of the output, and calculating this function, this normalization part is intractable in general case. Okay, this is the partition function that which is intractable to calculate for general energy function. We know that the energy is this neural network. This is the neural network that provide you with the energy, and then the exponent of the minus of this value is the probability for this x. But we know that this output is not necessarily normalized, so it is not a probability density function. I can add a tilde here for a better clarification. Okay, let's continue. And we know why we need the normalization. Why we need the output of energy-based model to be normalized, because when it is normalized, it has a limited budget, and it must put that budget on the meaningful data, not spurious peaks. Okay, so we need this normalization, and it is a property of any PDF function. We talk about why EBMs are great options. We see that they are really flexible, and you can almost convert any problem in machine learning, in different machine learning tasks, into a task which is suitable for an energy-based model. And then we talk about the Metropolis Hasting algorithm, which is a method to sample from these models, because we know that all we know about the model in an energy-based model is that if you input x, you will have something. You will have the exponent of the negative energy at the output, and this is not normalized. So how we can sample from something like this, assuming that it is trained? It means that it gives you high probability for samples coming from data in comparison to samples coming from other parts, because we know that the absolute value is not working here because it is unnormalized. Okay, the Metropolis Hasting algorithm is an algorithm to sample from such a model, and we talk about these two parts. We'll talk about them further in this presentation too. Just two important points is that you are at a sample x1 or for example xs, then you sample from a proposal distribution q, which is parameterized by xs. Then sampling from that, you have a proposed data point. You propose this data point to be a better data point, or a data nearer to the distribution. Then you have you calculate this alpha. Generally, we believe that just the first part, it means that the ratio of the probability is enough, but it is also the effect of the proposal distribution is also added, which is called Metropolis, which is called Hasting correction. We will talk about it further. And thus, at the output, whether or not this condition met, you will update your sample. So what are the notes about the Metropolis Hasting algorithm? First, about the proposal distribution, Q. The value of alpha, we see that it is calculated in this way. This factor is high when the new proposed sample is has better probability in comparison to your previous sample, and this value, I think we have the name here. Yeah, the first term in RHS compute the ratio between likelihoods and increase the acceptance of XP when the likelihood ratio increases. We know that here. It means that any sample which is more probable is more probable to be accepted. The second term in RHS, known as Hasting correction, this correction calculates how favorable is the proposed sample in terms of your Q distribution. If it is favorable in terms of Q distribution, it means that it is not a great point. It is not favorable in terms of your unnormalized density. So it should be corrected, as we see an example in the previous session. So this calculates how favorable the new proposed sample is in terms of Q distribution. Okay, a proposal distribution must meet the property of must covers the support of the target distribution. It means that if you know the support of your p theta, it means that you know that your theta distribution covers, for example, positive parts of the real number in the one-dimensional case. Okay, this is the cover of your p theta. We know that the cover can be found both with normalized and unnormalized functional form. So it is not important that the function is not normalized. So you find the cover, and then your Q distribution should be such that if you take the union of the support of this proposal distribution, for different values of condition, it means that your current sample, then this should be cover all the support of the your original. Why should this property? Why should we have this property? It means that all the points in the support of the unnormalized distribution must be accessible. You know, if that point is not, for example, assume that there is a part in the original distribution, in the unnormalized distribution, where for any x, the support, the value of the value that Q gives probability other than 0. It means the support means, let me, a simple definition for the support, assume that for Q is the value of x such that Q of x is greater than 0. It means that they have probability to be selected. Okay. What does this property, what is the object of this property? It is that any point in the support of your p theta distribution, your unnormalized distribution, must be accessible using the Q proposal distribution. If the Q distribution cannot cover this part, it means that you will never ever see any samples from this part. And it is evident that sampling from Metropolis Hasting algorithm will not converge to the true data distribution, because the data distribution is non-zero here, but you will never generate samples here. Does it make sense? Okay, this is the first property. The second is that if you can also select your proposal distribution to be independent of your current sample. It means that the QX condition on XS is Q of X. And thus the resulting method is known as the independence sampler. We know that for the independent sampler, it is much more simpler, but it may not be efficient in practice. Okay. Another property is that if you select Q such that if you select Q using this form, the resulting algorithm is known as random walk Metropolis algorithm. And also in several cases, such as this case, you have the property that because the distribution is symmetric, you have the property that the Q of xs given xp equals the Q of xp given xs, and as a result, your alpha value will take this simpler form. We know that when it is symmetric, the second part will be equal to 1, so the alpha value, just pay attention to the likelihood, to the ratio of the likelihood of the samples xp and xs, yes.
The second bullet point, are random walk Metropolis Hastings algorithms, or I guess the third bullet point.
Third, okay.
So RWMs, is that the case whenever it's normal or whenever P conditional and then the reverse conditional are equal to each other?
I can answer. What is your question?
What makes it a random walk Metropolis algorithm? It just has to be normal, or it has to be the second, or it has to be the fourth?
No, just to be normal is enough to be a random walk Metropolis algorithm. Yeah.
Is it only normal distributions, or can there be other distributions that are symmetric that also make it random?
Because in the random walk, we generally use normal distributions to generate our next movement. So it has resembles the random walk algorithm. So they call it random walk Metropolis algorithm, just because of the resemblance with random walk algorithms. Okay. When using Metropolis Hasting algorithm, initial samples, we know that initial samples are not coming from the true data distributions because you have some turbulences in the start of your algorithms, and thus those samples are known as burn-in samples, and they are usually omitted from the samples because they are not coming from the true data distribution. But the problem with Metropolis Hasting algorithm is that you cannot define an iteration t that after t the samples are coming from the true data distributions. We just know after enough iterations the samples are coming from the true data distribution, but you do not know the exact value of t. There is not a closed form for this value of t. For example, after this t you have some. It is especially the movement from the start turbulences to the true data distribution is very smooth. It means that you cannot maybe define exact value for this t. So this is an example for the Metropolis Hasting algorithm. This is an unnormalized distribution. You see that the distribution is unnormalized. This is the summation of two, I think, normalized distribution. So the area on the curve is more than 1. And then this is the result of samples coming from the Metropolis Hasting algorithm. The property for this simulation is that the unnormalized distribution is this one. It is clear that it is more than 1, the area on the curve. The number of samples generated is 10 to the power of 5. And the burned-in samples are 10 to the power of 3. And the proposal distribution is a normal distributions with variance equals to 1 and around the sample you have. You can find the source code here and also some other examples. As you can see, we know that it is very simple because it can easily be normalized. But think of general case where you have, for example, 1 million dimensional random vector, and then you want to sample from that, and the output is an image, because, for example, it is trained on face images. It is a very hard task, but in this simple example, you will see that the Metropolis Hasting algorithm generates samples exactly aligned with the unnormalized distribution. Any question about the Metropolis Hasting? Okay. Now let's talk about the cons and pros of Metropolis Hasting algorithm. The pros. First, Metropolis Hasting can sample from an unnormalized distribution. So if you have any method that you can train an energy-based model, then Metropolis can sample for you from that distribution. Metropolis Hasting algorithm guarantees to converge to the target distribution irrespective of the initial point under mild conditions. One of those conditions is that the Q distribution is such that all the part of the unnormalized distribution is accessible. So selecting that Q is an important part in Metropolis Hasting algorithm. The next one is that based on the problem, you can design your own proposal distribution that can work better. And the cons are, first one is if you select a bad proposal distributions, then you have a very bad convergence rate. And also you do not know when you can confidently say that the samples are coming from the true data distribution. So selecting that proposal distribution is very important. The generated samples, this is very important. The generated samples by Metropolis Hasting are correlated. It is very important. You know, in general cases, for example, when you want to estimate a KL divergence using samples coming from the distributions, you need independent samples, okay? But in the case of Metropolis Hasting algorithm, you know that the samples are correlated because condition on XS, you calculate XS plus 1, and XS plus 1 is calculated. So the samples are correlated. And if you want to have independent samples, you should start your sampling from different points, and the result of them is independent. Does it make sense? Any question? Okay, it needs burning period to converge to the target distribution. So some of the samples are useless, and it is challenging to assess the convergence of the chain to the target distribution. You cannot definitely define that t-value that after that value you are confident that the samples are coming from your unnormalized distribution. Okay, now we want to, we just talked about two algorithms to sample from an energy-based model. Then we will see another extension of the second one, which is used for some types of diffusion models. So now we want to conclude our discussion about the Metropolis Hasting algorithm and start the second one. Any question about Metropolis Hasting? Yes.
The something that would make sense. My question is on how do you optimize the network that eventually gives you the...
Yeah, that's another problem. You know, we will talk about now we just assume that you have a trained model. Yeah, that give, for example, high probability to more. You can just calculate the ratio of the probability using that model, because it is unnormalized. Yeah, we will talk about the contrastive divergence next, which is a method to train energy-based model. Yeah. Okay. Now, what do you think? What is the problem with Metropolis Hasting algorithm? You have access to E theta of x. And it seems that you do not use this E theta of x, and especially its gradient, in your process to generate samples. You just use a proposal distribution Q, and that proposal distribution gives you a new sample, and then based on the value of the ratio of the likelihood, you decide. But you have more information about the distributions, and that information is that the gradient of this E theta, which gives you some information how you can increase your likelihood. This gives you a direction. We know that the exponent of minus this term divided by the integral of the above. This is the true data distribution. Okay? If you take the gradient of this side and this side, excuse me, assume that I calculate the log likelihood, so the logarithm. What happened? So because I have the logarithm here, it equals the logarithm of the denominator, and the logarithm and exponent cancels each other. I have minus e theta of x minus the logarithm of the integral of that term. This is the logarithm of your normalized model, okay? If I take the gradient here with respect to x, I want to know how I change x so that the probability will be increased. So I take the gradient with respect to x, okay? I add the gradient here, I add the gradient here. Oh, sorry. Yeah, x. All of them are x. We do not, the model is trained. Assume the model is trained. Okay? This, what does this direction gives? This direction gives the direction that you can follow to increase the probability. Yeah? This is the gradient. What is this value? Can you calculate this value? Assume that you have the model. You can easily calculate it with any of the libraries you know. And what is this value? I write it here again. The gradient with respect to x of the logarithm of the integral of the exponent of minus energy. What is this value?
So constant.
This value is, does this value dependent on x?
No.
No, so the gradient is 0. So, based on the energy, you have exactly the direction that you can use to increase your likelihood, the log likelihood. It is not important because log is a monotonic function. Does it make sense? Yes.
So you're assuming that we have a trained model because you do not change it, that's all.
Yeah, yes.
Yes. You have a trained one. Why increasing the probability of a trained model? Like, why do we need to?
With respect to x.
I know. Why? Why do we need to get the gradient of x?
Yeah. Assume that I have something like this e theta of x. I have e theta of x. We agree that I have a trained model. Okay. I have e theta of x. So I want to start this e theta of x is corresponding to a distribution, but I do not have the distribution. I want to take samples from this distribution. I want to take samples that are coming from p theta of x, but I do not have p theta of x. So what can I do? One solution is that I start with a random point x0, update this x0 to x1 so that x1 is a better, higher probability samples from p theta of x. X is changing. You know, the direction in x domain is important now. The theta is not important because the theta is assumed it is trained. We see that Metropolis Hasting algorithm using a Q distribution to propose a new XP, and then based on some criteria you whether accept or reject this XP. But now we want to use the information in this the gradient of e theta, gradient with respect to x, this value, this way, the gradient with respect to x. Why? Because we know that direction will increase the log likelihood. So I update x using the minus gradient with respect to x of the energy. In other words, I am decreasing the energy in that point. Means that in the if you decrease the energy, it means that you are if you decrease the energy, you are increasing the probability.
So in this case, you're sampling from
We see that it has some corrections too. It means that you just, if you just follow this direction, you will converge to the peak and you do not sample from other parts. But you have some randomness that result in sampling from all the parts of the distributions based on their likelihood. Any question? Yes.
So how do you accept and reject?
Yeah, this process has its own way to accept or reject the data. Yeah. Any question? Okay. So now, what is changing? The way that we update from x0 to x1, it is changing from the proposal distribution to some information coming from the gradient of the energy function with respect to x. Pay attention to this x. You generally have the gradient with respect to the model parameters, but now you have the gradient with respect to inputs. Yes?
What is the intuition of what energy is representing?
Energy, conceptually, it is aligned with the concept of energy in physics. As I talked about in the first part of this presentation, that there are also alignments between energy-based models and statistical physics. That energy is exactly aligned with the concept in statistical physics and energy in the physical concept. Okay, we know that the calculated direction minus the gradient of with respect to x of the energy result in decreasing the energy or equivalently increasing the likelihood, or better, increasing the log likelihood. Okay, so we use we can use this direction to propose a new sample. Instead of a proposal distribution, we use this direction to propose a new sample. The algorithm is called, the general type of algorithm is called Hamiltonian Monte Carlo algorithms, and use the information of the minus the gradient of the energy to generate new samples. There are the general family of the algorithms. We talk about one of them. Okay, there is some resemblance between these algorithms and statistical physics, and as we talked before, this slide is not very related to our discussion. Do you have any questions? No. Okay. But just to understand the resemblance, we talk about some concepts coming from the statistical physics. In the Hamiltonian Monte Carlo, which is inspired from the statistical physics, sampling method uses a function which is called the Hamiltonian function. The Hamiltonian function is your energy function plus a term which provide you with those randomness. Assume that the Q distribution provide you with some type of randomness here, that K of V provide you with those randomness. The E theta of X represent the potential energy at point X, and the K of V represent the kinetic energy at a speed V. But in a statistical setting, this is the concept in physics, in a statistical setting, we have this E theta of X. We know that it is the minus the log of the P theta of X, and P theta is not necessarily normalized. This is exactly the concept of minus E exponent of E theta of X equal to P theta of X. And the kinetic part represent the negative log likelihood of the Gaussian distribution. So pay attention to the fact that it is aligned with the distribution, the Gaussian distribution. So and that Gaussian distribution provide you with the randomness in your algorithms. Similar, assume that you select something like a normal distribution for a Q. This term wants to play the role of that Q. We just talked about the Langevin Monte Carlo, also known as Metropolis adjusted Langevin algorithm model. which is a special case of Hamiltonian Monte Carlo, that is this algorithm. This is a special case. This is the general case of Hamiltonian Monte Carlo algorithms, and we just talked about the Langevin Monte Carlo. Okay, what does the algorithms follow? It starts with a sample x1, and for s1 to t, you first sample a momentum, Vs, from normal distributions. Pay attention to the sigma, which is aligned with the definition of the kinetic energy. They are selected. You select this sigma matrix to sample momentum from. Then you update your samples in this way. This part is a corrected, a direction corrected by your sigma value, and this part provides you the randomness. You see, Vs is coming from this normal distributions, and there is also a step function, a step size eta, which is used to measure the distance you follow in each step. And also you update your speed in the sense of that statistical physics, and update your speed in this way. So you have an updated proposal point, you have an updated proposal v vector. Then you will calculate A as follows. This is exactly the same as the way that we whether reject or accept the new points. I made a mistake here, I think. Let me check it. Yeah, I made a mistake. This is x. This is xp and this is xs. I think this is the problem. I will correct this algorithm and send the corrected version. So we know that what is the value of this h function. The h function is defined here. The k, the energy is defined as this term, and the k is defined as this multiplication of these three vectors and sigma value. So you can calculate these two terms and calculate A, and then A is used to correct whether accept or reject the new sample. Based on a new random variable u coming from a uniform distribution, you whether accept or reject the new points. And we see here that it is using, assume that sigma is a diagonal or is identity matrix, then you will see a very simple form here. It means that xs takes steps through in the direction of minus the gradient of e theta. I should add an x here to emphasize that this gradient is with respect to the inputs, not the model parameters, and also here. So you take steps in the direction of the minus gradient of e theta, and then add some randomness to that point. Because if we just go toward this direction, we will end with one peak of your distribution, and you will not cover all parts of the distribution. And this randomness is designed such that the resulting algorithms after enough steps will converge to your true data distributions. This is the new algorithms to sample from an energy-based model. It is more efficient in terms of converging faster to your true data distribution. Any question? Any problem with the formulation? You can see how they are proved to be convergent and converge to the true data distribution in the references I introduced, and I think especially in the Kevin Murphy's book. Okay, so if you have a trained model, you can use MALA or this Langevin Monte Carlo algorithm to sample from that distribution. Any question? Okay, this is an example of the Langevin Monte Carlo algorithm. As you can see here, these are samples coming from the true data distribution, And this is the result of Langevin Monte Carlo algorithm. As you can see, the density is almost equal to your true data distribution in all parts except the low probability parts, and which is due to the limited number of samples you have in your LMC. This is the LMC for the banana distributions. This distribution can be downloaded, I think, using one of the packages in Python. You can easily download the distribution and sample from that distributions. The number of samples is 10 to the power of 4, and the burned in samples is 200. You can find the source code here. And yes?
Can you go back to almost that back?
Yeah.
So X and V, they're just like unitless numbers, right?
What?
They are unitless numbers, but because I'm trying to do some like dimension analysis of them, get some intuitions.
You mean their dimension?
Yes.
Their dimension is the dimension of your random vector. For example, if you are working with images, they are 1 million. For example, if the images are 1000 by 1000, these are both 1 million by 1 million.
Okay. And they're just numbers. There's no unit to it. Okay.
Unit?
Yeah, like meters.
In the statistical physics, everything have its own definition. You know, this is the summation of potential energy and kinetic energy. Okay, but in terms of statistics, maybe we should think of what is but the result of this formulation must be the same unit as your x. Yeah, when you focusing on each part, maybe a bit harder to understand.
Because like if they have units, like each part has to have same units, right?
Yeah. No, I mean, for example, think of these distributions and their concepts. For example, the momentum generating distribution. But because they are adding and subtracting, they must be of the same unit. Yeah, each part separate. Okay, any question? Yes.
Can you explain like how burn-in samples are those like you take like 200 steps before you get a good sample, or just
what do you mean? Why we need to burn some samples? You know, because of the starting point effect, you need to burn them. For example, assume that I have an unnormalized Gaussian distribution. Okay, I have unnormalized Gaussian distribution such as this distribution is very peaky around. It means that it has very low variance. Okay, then I start my sampling process from here, x0. Okay, then there are lots of samples here. And then I will reach this point, this high probability area. Okay. Those samples, if you consider those samples as samples coming from the true data distributions, it is a problem because these parts are very low probability in terms of your distribution, okay? But if you crop them, if you burn them, put them out, then the resulting, after some iterations, the result is coming from the true data distributions. But if I sample from this part, I may result in something like this, for example. It's not different. Excuse me. If I plot the histogram of the samples, I may have something like this. If I do not burn, okay? Why? Because these samples are generated due to the transient of that chain. In those transients, it is not following the true data distribution. It's just sampling so that it can converge to that distribution. It is not convergent yet. It converged yet. So you have some samples here, while the true data distribution give very low probability here. Make sense? Okay, great. Yes.
Can you go back to the optical?
What?
Can you go back to the previous slide? So, what is, for when we're updating X usually, what is the term we're subtracting off? Like, what does that represent?
What is?
What is so in the updating access in VS?
Yes.
What are we subtracting off? Like, what does that value represent?
I think take a look at the proof of the convergence of this algorithm may provide some intuition that why we also should decrease, we change V in the direction of the gradient of the energy function. You are following the same direction as you are following the direction which increases your probability. Maybe we should take a look at the proof why we should follow this direction. Yeah, and we gain intuition about the direction. Yeah. Yes.
So you're going to correct for gradients twice.
What?
I'm a bit lost the parentheses. So you're going to create, you're going to subject the direction of the gradient, and then you again calculate another set of gradients.
This is the update for the v vector, and this is the update for x, and both of them are needed to calculate a for the updated point. I have a problem here. I said that this is x p, this is xs. I have a mistake there. Yeah, both of them are needed to calculate a. Yes. What? That is step size parameter, and it should be selected, yeah, as an hyperparameter. Yeah, and play an important role too. Okay, so as you can see here, you can easily sample from a two-dimensional distributions using just 2000 Bernin sample. And so it is very efficient in terms of sampling from high-dimensional distributions in contrast to our previous algorithms, which was Metropolis Hasting algorithm. Okay, what are the cons and pros for this algorithm? The pros is that LMC is more efficient than MH in high-dimensional data, and this is our application. We generally work with high-dimensional data. Assume that you train an energy base for the images. Then you want to sample from, for example, a 1 million dimensional random vector. And in that case, this algorithm is much more efficient than Metropolis Hasting. LMC utilizes the gradient information and does not need proposal distribution, so you do not need to worry about the proposal distribution. LMC is also guaranteed to converge to the distribution under certain conditions. And the cons is that the LMC requires the gradient computation, so you should backpropagate through your network using any library you generally use. So it is more complex than Metropolis Hasting. In Metropolis Hasting, you just sample from a proposal distributions, but here you need to take the gradient of a, for example, neural network with respect to the inputs. LMC is sensitive to the eta, which is selected before starting the algorithms, and LMC may struggle with sampling efficiently from distributions with multiple modes and may trap in a local mode. Trapping in local mode is something similar to mode collapse in GANs. You trap in a mode. You generate samples from the same point, so you have similar samples in terms of visual concept in a model trained on images. And also similar to Metropolis Hasting algorithm, here is also challenging to assess the convergence of the chain to the target distribution. Chain, I mean, because all of them are Markov chain Monte Carlo algorithms, chain is coming from that definition. So now we know that how to sample from a model that provides you with unnormalized distribution. So how we can train them? This is the new problem. how we can train. Assume that I have a neural network. That neural is very flexible. It accepts X as its input, outputs one value, and that value is positive because it is minus the exponent of the minus energy. How we can train them? Contrastive divergence is a method to train a model using is a method to train those energy-based models, and we will talk about it now. It is the basis for different, there are some other types of these algorithms in the literature, and you can follow them. What is the first one in this respect proposed in the literature? So I focus on this algorithm, and then you can easily extrapolate your knowledge here to understand other type or variants of this algorithm. Okay. We know that we generally are in the likelihood-based training. We use likelihood-based training algorithms, and the approach is to maximize the likelihood that the model gives to a bunch of samples, which are your training samples. So the most important and challenging part is that I need the gradient with respect to the model parameters. Pay attention to the model parameters of the log likelihood to the model. We are not talking about the X anymore, because we want now to train the model, and we need the gradient with respect to the model parameters. So let's take the gradient of this log likelihood. We know that in an energy-based model, you can have the normalized distribution using the unnormalized distributions divided by the partition function. It is clear how you can convert this to this one, and if you apply the logarithms to this ratio, it is as I write it here before, you have the logarithm of the numerator minus the logarithm of the denominator. Because the denominator has an exponent, the logarithm and the exponent cancel each other, so you have the minus gradient of energy with respect to the model parameters minus the logarithm of z theta with respect to the model parameters. Can we say that here it is 0 again? Yes or no? No, because z theta is a function of theta. It is not a function of x, because x is integrated out, but it is a function of theta, so you cannot delete it or make it 0. And this is the most important challenging problem, because taking the gradient of the first part is very easy. Both with respect to x or theta, it is easy to take the gradient of energy function. But taking the gradient of the logarithm of the partition function is very complex, because the partition function itself cannot be calculated, and it is intractable, not easy. Any question? So we need to focus on the second part. This is the justification for each of these equalities, and we need to focus on this part to see how we can calculate it, because the first part is very easy. Okay, let's revisit what do we have in the gradient, the gradient of log of z theta. We know that z theta can be calculated using the integral over all possible x values on the output of the model network, energy-based model. The gradient with respect to the model parameters of logarithm of something equals the, we know that if you have log of u, let's, I think, continue on the slides is much better. I write down the property here. This property, the gradient with respect to theta of the log of any function of f equals the f theta inverse the gradient of f theta. I use this function in this part. So we have this value. This is the partition function to the power of -1. And this is the gradient with respect to the model parameters of this integral. In the second part, I apply this gradient into the integrand here. So we have this result. The equality I use here is written at the end. And then if I put this integral under this first part, exponent of minus e theta of x, I have something like this. I just put this under this part. I can put it inside because it is independent of x. X is integrated out here, okay? It's better to write x prime here so that you do not confuse it with x. I will update it, but pay attention that the complete integral, the result of the integral is independent of x, so I can put it inside. I put it inside, and I have something like this. What is this term?
Theta.
Yeah, this is a normalized distribution. Just pay attention that this x is not the same as above. I will change it. This is just a number, this denominator. So I put it here, and at the result, the exponent of minus e theta divided by this number is the normalized distribution, and it is valid PDF. So I replace it with p theta of x times minus the gradient e theta minus with respect to the model parameters of e theta and integrate out over all possible x values. What is this definition?
Expected value of gradients.
Yeah, exactly. Something times the distribution, the PDF value, and integrates over all possible x. It is an expectation. It is the expectation of this function, everything which is here. So we have the expectation with respect to data coming from the true data distribution through unnormalized data distributions of this gradient, minus the gradient with respect to the model parameters. Does it make sense? Everything is clear here? The above two equalities, A and B, are following from these two the properties of differentiation. Any question?
And then we can use Monte Carlo, right?
Yeah, then we need Monte Carlo, Markov chain Monte Carlo to sample from this. You?
So the point where you said like x's are different, at step B, it just looks like you're applying the chain rule.
Yeah. The things that I apply is written here. The properties that I use to change them is written here, okay? But the things that I talk about here is that this is a number. Do not pay attention to this x which is aligned with this x, okay? This is a number. I put this number below this exponent of minus e theta. I know that this is the normalizing partition function. I know that. This number is partition function. If I put it below exponent of minus e theta, then distribution is normalized because that's exactly the partition number, partition function, okay? I just put the number here. I will change this x to x prime when I update the presentation. Just not to confuse it with this x. They are different because it's integrated out.
Yeah, do you mind explaining that again? Because that's the part I don't understand why it's different.
No, exactly. A is coming from this property, okay? A is coming from this one. So I have something like, I write it as z theta, okay? Z theta minus 1. Is it important to write it z theta or this integral? Because it is exactly z theta, okay? I write it z theta to the power of minus 1, the gradient with respect to the model parameters of this integral, exponent of minus e theta of x dx. Okay? What happened next? What happened next is that I put this gradient inside this and take the gradient of this integrand, and using the property number b, I update it as this one. Z theta minus 1 integral of exponent of minus e theta of x times the minus gradient with respect to theta of e theta of x. This is just the application of chain rule in differentiation, okay? Now, this is this constant, so I can write it as this one. And because it is a constant, it can be put inside the integration, z theta. Does it make sense? And this value is the true normalized distribution. Do you have a question? Yeah.
So this P theta x is the normalized version.
P theta.
Yeah.
P theta x is normal.
So our problem was that we didn't have this normalized version of
Yes.
this. So how are you going to sample from this?
The Langevin Monte Carlo, Markov chain, all of them sample from this. You do not have access to P theta of x, but you have access to E theta of x.
Yeah. Like, weren't this LMC or MH4 the unnormalized sampling?
Yes.
But this is this normalized.
Yeah, I know. They sample from P theta of x with unnormalized distribution. It means that accessing to this to this value, to this function, although it is not normalized, when you apply, for example, Metropolis, Hasting, or LMC for this function, you are sampling from the true data distribution, although it is unnormalized. If you have access to the normalized one, everything is very simple because you can easily sample. You do not have access to the normalized one. Instead, you have an unnormalized version. Using that unnormalized version, you can run MCMC over unnormalized. Then it generates you with samples from the true data distribution. This is the power. They sample from an unnormalized functional form.
So I thought that LMC or like MH will mimic the shape of the unnormalized distribution.
That's the histogram, okay?
Yes.
That's the histogram. It means that the samples are coming in terms of histogram is exactly similar to the shape of the unnormalized distribution, okay? But the important part is that after the learning period, you have something which is you are confident that it is from the true data distribution. And in general case, for example, here you just need to be confident that you have samples from the true data distribution to calculate this expectation. Okay? Any question? Okay, so we convert this gradient of the log of the normalizing partition function into an expectation. What can we do now? What can we do with this expectation? Yeah, we can use Monte Carlo estimation. You have an initialized model. You can sample from that model, update this, calculate this expectation, and based on the previous slide, you have the first term. Then you have a gradient that show you how you can update the model parameters so that the likelihood will be increased. And it is the direction of learning because you are increasing the likelihood over your training sets. Okay? So, this is the idea. We sample from an EBM using Monte Carlo or Langevin Markov chain. These are the samples, and we know that these samples should be independent, must be independent. So you should run several Markov chain Monte Carlo method to sample this XS, and then calculate this gradient of the partition function using those samples. For the first part, you can easily sample in your starting point. Okay, but there is a challenge. The most important challenge is that the first one is that the MCMC generates correlated samples, so all the adjacent samples cannot be used in the calculation because these are correlated samples. You cannot use them because assumption in the Monte Carlo estimation is that you have independent samples from the distribution you are expecting. You are calculating the expectation. Okay. For example, when we use something like in the autoregressive models, the log of p theta of xi 1 to n, this was equal to the expectation. The expectation of the log of the p theta of xi from the xi coming from the data distribution, okay? Because the samples selected from the training set, we assume them to be independent, we can write this equality. But when they are not independent, you cannot use Monte Carlo easily. So this is the first problem. It means that you cannot start one Monte Carlo sampling method and then use all of the samples after the Berlin to calculate that expectation. It is not. It cannot work because the samples are correlated, and you cannot use Monte Carlo estimation using correlated samples. So you need, for example, assume that this is the Berlin period finished at t equals to 10 to the power of 3, okay? Then from this point to the end, everything is coming from the true data distribution. But if you use this one and the next one, 10 to the power of 3 plus 1, they are correlated samples. They cannot be used, both of them, in this summation because they are correlated. Sometimes you can. This is a practical solution. Sometimes you can wait for an enough number of iterations, for example, 2 times 10 to the power of 3. Then you can use these samples because the correlation is very small between these two samples because the length is very large. But instead you can start several Markov chain Monte Carlo methods in parallel. For example, the first one, the second one, and each of them use, for example, the samples at the point 10 to the power of 3. Then you have independent samples, and then you can use them to calculate that expectation. Is it clear? Yes.
Does this satisfy like the Markov property, like given the present and independent past?
And the Markov property said that based on the degree of the Markov chain, given the past, you can predict the future. Okay, you can you can calculate the distributions over the future. This is the Markov chain property. In this case, because this distance is large enough, we can assume that they are independent, but in practice they are not independent until the end. But the correlation is very low in between these two samples, and both of them in practical settings can be used to calculate that expectation. But the best option is to run several Markov chain Monte Carlo methods in parallel. For example, you want to estimate this, you want to estimate it using 10 samples or 100 samples. You run 100 Markov chain Monte Carlo algorithms in parallel, for example, Metropolis Hasting algorithm, and then after their Bertin, you use the resulting sample to calculate the expectation. Okay, for example, I use 100 of these Markov chain methods, and at the output, each of them generate one of those x tilde of s. And then I use these. I know that they are all coming from the true data distribution, and they are all independent. Why? Because their start is independent. Okay, and then I use it to estimate this expectation. Does it make sense? Okay, yes.
So I don't understand why the two adjacent samples are correlated. Like, what is the correlation meaning in this context?
Yes. It means that assume that if I give you the previous samples, what is it? You know, the correlation to some extent we talked about independence. Okay, if I give you assume that in a Metropolis Hasting algorithms, I give you the information that x s equals xs equals, for example, 2. Okay? Does it change your intuition about what are the probable values for x plus 1? It changes, yeah? So they are correlated. There is an information path between them. Any question? Okay, so there are two severe problems with these methods. The first one is that you should run, for example, for the best case, you should run several Markov chain Monte Carlo method to sample this XS. So it is very complex and resource consuming. Okay, because each of them needs the burning period to convert. After that, you just have one sample. Okay, you can use this idea, but assume that we are using the perfect option. Second, you cannot assess the convergence of Monte Carlo, Markov chain Monte Carlo methods. In terms of something like diffusion that we will talk about later, you will see that you start sampling and then update your sampling, and then visually you understand that the sample is converged because it is an understandable concept. Okay, but here you want to run an algorithm for training. It means that each time for just one update, you need several Markov chain Monte Carlo method to be run to update for your update, and then you do not know whether, for example, this number is enough to weight or not. Maybe you do not select your proposal distributions very well, then you need to weight more than this number. For example, you need to weight until 10 to the power of 4. And this is another problem. And this affects your performance heavily. If you do not sample from the true data distributions, it is not, your update is not acceptable, and you are doing something wrong. Okay, it means that this expectation is not calculated. This expectation is not calculated. Sorry, I have another problem here. No, it's okay. I think it's this there. You cannot calculate these gradients, so everything, your model will not work. So Markov using one of MCMC models to calculate the gradient is not an option, is not an efficient option or a practical solution. Contrastive divergence is an approximation to the maximum likelihood so that you can easily train your model. What is this approximation? In this approximation, you do not need to calculate the gradient of the log of the partition function anymore, which is the problematic part. And you can use the sample in the tth iteration of any MCMC sampling method. Our problem is that we do not know until when we should wait to use the samples of the Markov chain Monte Carlo. But in the contrastive divergence, you will see that you can select any of the samples in any t, in any index of your Markov chain Monte Carlo method, and it can be easily equal to 1. It means that you just run one iteration of Markov chain Monte Carlo and then use the samples to update your model parameters. We will see now how it can be used. Just this block, and then we will finish our discussion today. Assume that X is a samples coming from P theta. This power T shows that you run a Markov chain Monte Carlo to sample from P theta of X, but you just have T steps. any of them, for example, LMC, for example, MH, any of them, in all of them you start with the initial sample x0, okay? Then, for example, using Q distribution, proposal distribution, you propose something like, I think, yeah, x0. We propose something like x prime 0. This is the proposed one. It is whether accepted or rejected. Accept or reject, and then we have x1. Okay, this is one complete iteration. For example, in Metropolis Hasting. Okay, if this data is coming from the true data distribution, can this data come from the true data distribution or not? Can I select the starting point, a sample which is coming from the true data of this distributions? Yes or no? How? Yeah, exactly, the data set. I use the data set to sample x0, okay? Then I know that this data is coming from a distribution. It is not important what is that distribution.